One more mass spring example problem. On your first trip to planet X, you happen to take along a 145-gram mass, a 40-centimeter-long spring, a meter stick, and a stopwatch. You're curious about the free fall acceleration on planet X, where ordinary tasks seem easier than on Earth. One night, you suspend the spring from the ceiling in your room and hang the mass from it. You find that the mass stretches the spring by 31 centimeters. You then pull the mass down 10.6 centimeters and release it. With the stopwatch, you find that 10 oscillations take 15.5 seconds. Based on this information, what is g? So g, remember, is our free fall acceleration. On Earth, it's 9.8. Here, we're trying to find what g happens to be on this planet. We would expect it to be less than 9.8 if they tell us that the ordinary tasks seem easier. So let's go ahead and draw a sketch. I'm very visual. So I hang this mass. The spring. I'm told this spring is 40 centimeters long. From the mass, from the spring, I hang the mass from it. So it tells me when I hang this mass, this stretch is 31 centimeters. So I am assuming this means this is the equilibrium position because it's not yet oscillating. I have to then pull the mass down more to release and then have it oscillate. So the next step from equilibrium is that I pull the mass down even farther, this distance of 10.6 centimeters. I release it, and then I observe that there's 10 oscillations in 15.5 seconds. All right. So from this first portion right here, the spring itself is 40 centimeters long. I hang the mass from it, and I see that it stretches 31 centimeters. In equilibrium, this mass has the spring pulling upwards and the force of gravity pulling downwards. So the magnitude of the spring force pulling upwards has to equal the force of gravity. I know X in this case. The spring is stretched by 31 centimeters when we hang the mass from it. I know the mass is given to me up here in the problem. I'm going to go ahead and write that out in kilograms. But I do not know g because we're not on Earth, and I do not know k. So I'm kind of stuck for a second. So let's talk about the oscillations. I know in an ideal mass spring system, I'm going to come over to the left here. When a mass spring system is oscillating, omega is the square root of k over m. Omega is also 2 pi f or 2 pi over t. All right, so 10 oscillations in 15.5 seconds. F is the oscillations per second. So I can totally figure out the frequency. Or period is the number of seconds it takes to complete the number of oscillations. So I can use either one of these. I can't say that either one is better than the other. Coming back to my equation, I'm going to go ahead and just use the 2 pi f since they're already close together here. If I take the square root of both sides, sorry, not the square root. If I square both sides, I get rid of the square root. I know the mass, so if I bring the mass up here, we can calculate the spring constant. So by putting in our mass, 2 pi, our frequency is the 10 oscillations in the 15.5 seconds. That whole 2 pi f needs to be squared. So 2 pi times 10 divided by 15.5, square that. I find that the spring constant, 2.38. Now again, I want to take this out a few digits because I'm not at a final answer. So by analyzing the oscillations, we're able to figure out what the spring constant is. Now we can come back here. G, solving this equation for G, I'm going to have kx over m. This x is specifically the distance the spring stretched to this new equilibrium position. So the 31 centimeters. It's still the same mass. All right, so 5.09. Now I know the units should be meters per second squared. Let's make sure we see where those units come from. Oops. So K is units of newtons per meter or kilograms per meter squared. X is in meters. And then M is in kilograms. No, is that right? No, it's not. K is in kilograms per second squared, not meters squared. The kilograms cancel. This is where our meters per second squared comes from.